so we see it.
Great. Okay, so for whomever is new today for the first time at this course, this is a series called Get Started in OpenSees with STKO. We're starting really from scratch. I've seen some faces of people or like names of people that have joined previous webinars of ASIA software. I'm sure some of you guys are very advanced with this, but this is a series for starting really from the beginning. We divide it like this. So we start with the 30 minutes presentation from me, and then we have a large slot of time dedicated to questions. Normally there's some assignments, and then you can join the conversation on our forum. We've just done sorry, I just had to admit someone. We've just done really few introductions on the forum. So just if you need help with OpenSees and STKO during the time of this, please just use the forum to ask any questions. And support material will be available at this link. You guys will have all information and all materials that we are sharing with you during the classes. So here is the page where you can sign up for the next courses. If your friends wants to join, if you signed up once, you will always receive the email for joining the next class. And here are the classes we already did: Introduction to OpenSees and Introduction to STKO. You have a description of what we did, and from here you can download the files. And here you can watch the YouTube videos recording of the class. So going back to my presentation, as I said, we've done some introduction, and today we have a class on the definition of a model, the overview of the definition of a model in STKO, in OpenSees with STKO. From next week, we're going to start diving into more theory topic, let's say. So we're going to analyze each and every one of these elements more in detail. Let's say not using a whole building model, but actually focusing on the specific subjects. Instead, today, I'm just going to give you an overview of an overall model. So we're going to talk about STKO interface, the pre and the post processor, how you should set up your workflow in STKO, and of course, an overview of the model. There's going to be actually two models, an elastic frame structure, and I should have added here, also a nonlinear frame structure. Just for people that maybe this is the first time you are here, these are the instructions for installing STKO. I just copy pasted them here from the last lectures so that you don't have to download the old presentations if you need. Remember, you need to install OpenSees because STKO does not embed OpenSees. So going forward, this is our STKO interface. I'm just going to show you the real thing now. Here it is. So we have our main menu, the main toolbar, the quick access toolbar, the work tree, the terminal, the script explorer, and the script editor. These are let's say the objects, the elements that define the preprocessor interface. Then we can switch the postprocessor interface. Same, we have our main menu, our main toolbar, quick access toolbar with a little less things, our work tree, and the terminal. Here, I don't know why it went on the sideways, and the editor, of course. Also here, you can access the script explorer. So all the tabs you can open and close by clicking on the X sign on the top right, and then turn them on again by right-clicking in the main toolbar and selecting what you need to reopen. So going back to our presentation, whoa, here we are. There's so many ways you can operate the same command in STKO. For example, if you want to hide something, you can click in the quick access toolbar, you can click in the main toolbar, you can hide a specific assignment by selection, you can just press function F4 on your keyboard, or you can program what you want to hide. So I will use let's say the ways I use the commands more often during these presentations, but just know that there's so many other ways that you can set up your workflow inside STKO. The first thing I want to start, as I always do, I want to repeat again that OpenSees does not have the concept of unit system. So I do this error all the time, almost every day. So it's been 1 day since I've done one arrow, and I've been counting them for every presentation. I will count them, and when I get to 5 days, I will just erase this slide. But I'm not very hopeful for it. So let's see in the next weeks what's gonna happen. If you want, from week 1, we have a TCL file that can help you to set up your unit system and just allow you to make conversions easier, in an easier way. And if you need, you can also, use the consistent union table that we provide here that can help you with doing some conversions. Whatever you do when you start a model in OpenSees with STKO or just in OpenSees itself, you have to define what is it that you're using for length, time, and force, and then derive the rest of the units. So any other quantities is a derived quantity. These are a few things that I wanted to make them pop a little about the preprocessor and the postprocessor, but I'm actually going to show them to you in the model. So just remember, there's a lot of stuff you can discover on the quick access toolbar. There's some mouse commands and shortcut keys that you can use to speed up your workflow. And of course, there's a color coding system in the work tree that you can also refer to and just use it to help you just define your model in the proper way. And there's also a lot of stuff in reference to the postprocessor. But anyway, this stuff is here in this slide just for you to have a reference for later. But what I want to this stuff I want to show you directly in the model, just not to waste time on it. Your workflow is set up as your, let's say, as the main toolbar is set up here in the preprocessor. You see all the tabs are referencing you to something that you have to do almost in this order. As I mentioned in the second week, whatever is you build up to the analysis step, it does not matter in the order in which you build it. Of course, you cannot assign a condition if you don't have any geometry, but if you first define a specific condition before another one, that will not really matter. Afterwards, after your geometry, you have your physical and element properties, your condition, of course, everything as a static or kinematic condition that you want to apply to your model, and the analysis steps. But let's get really to it. So this is the model I want to show you today. It's a 3D frame structure that we first model has elastic and later on has nonlinear with fiber sections. This is my unit reference system. Please, if you find error, tell me so that I can fix them. It's a 6-story building with a staircase model in it, with elastic beam elements and elastic sections. And we use this tool, which is the surface load, which is not often used because it has some limitations, but it's really powerful if you want to make a quick linear model of a large building. On this model, we did gravity and eigenvalues analysis and checked a few results. So given that I guess you guys will already have your STKO installed, I'm going to share with you the files for this model. Let me share them in the chat and you will tell me when it gets there. I just sent it to one person and now I sent it to everybody. Did you guys receive it? Okay, good. So if anybody has a problem in opening the model, just if it's really something like really quick, you can interrupt by any means, and then otherwise we can just see it at the end. I will share my screen again. And we'll open the model with you. So this is example 4 of our webinar series, of our course series. So first thing I do whenever I open a model is I set up the grid system in a way that will allow me to actually visualize better the dimensions of my model. And this is done through the quick access toolbar. So as you see here in the work tree, everything I already defined is there. And whenever I define something, a drop-down menu opens up to incorporate everything I define. First thing you do is define your geometries. For this model, we have one single merged geometry, and we have the control points, the control nodes, let's say master nodes of each of the floors. You can see if I zoom in here, yeah, let's do like this. Here you have our master nodes at each level. Okay, just so you know, everything that's not connected in your geometries tab in the work tree needs to be fixed or needs to be in some way. There has to be a condition applied to it, otherwise your model will be singular. Imagine it has a real building, you need to put a soil under it, something, and you need any floating elements needs to be fixed to something else, or let's say with an external condition. This is something that is not automatic in STKO, you have to define it yourself. Then we have the interactions. For this 3D frame structure, we defined rigid diaphragms interaction for each level. You can define these interactions separately or all together, depends on you. So what up to here, I would advise you all guys to, whenever you create a new model, to define your geometry before you go into any of these other sections. This is because a lot of weird things can happen if you explode, or if you move, or for example, if you do any of these, let's say, edit operations on your geometry after you have already assigned your physical properties, your element properties, and conditions. These things can get lost in the operations. For example, if you assign a local axis orientation, but then you move your model, these local axes can be lost. So a really good rule is to keep your geometry, like to complete your geometry completely, and even maybe assign the mesh to it if you want to check. This is something you can do right away. Of course, like you have to assign the element to, but you can check it right away and define it before everything else, because you will get not very good results otherwise. Then we have definitions. This is the time series that we use in our analysis. This can be done at the beginning, at the end, it doesn't matter. The first time you're gonna call for this is in your load pattern here. So whenever you do it, you can do it whenever you want. After that, we have physical properties. So I decided to differentiate just to show you that you can use more than one section in the same model. For example, we assigned a different section for the beam, for the longer beams, rather than for the shorter beams, a different one. This L-axis section can be defined like in 2D or 3D space with specific geometric characteristics, and STKO automatically compute these characteristics, and these are kind of useful. I will show you again, I will show you later why. So these sections were defined, and for example, if you want to assign the section to one of your elements, let's say I go here and I allow the selection only of the edge. This is one of the tools of the quick toolbar, where you can just turn on and off the things that you want to be able to select, so you can also not make mistakes. For example, let's say if this bin was in this, yeah, it was in this group. So if I want to assign, I just drag and drop, and the assignment is done. If I want to unassign, I just drag and drop and press Ctrl as I do it, and my assignment will not be there anymore. How can I be sure of this? I go in the property tab, color by physical property, and I will see different elements based on the different shader properties that I assigned to each of the physical property. Whenever you open a physical property editor, or also a condition or element property editor, you have a shader that you can define. You can define the color, the shyness, the transparency, a lot of different cool graphic things for each element. For this example, I color all the beams as orange and all the columns as green, but you can also differentiate more. So let's reassign this again, just to make sure. And to go forward, as an element, we assign an elastic beam column here. To see our element property assignments, we just click in the color by in the property tab, and we will see our color element assignments. Afterwards, we're going in our tab, in our condition tab. So, something that I forgot to mention that I wanted to show you here in the physical properties. As you can see here, I have some indices for everything that I create. STKO generates an indices. this is something that we do because we need to refer each element with a tag. I don't know if you guys have already modeled something in OpenSees, but you must have noticed is everything you define has a tag assigned to it. The tag can be an ID number or also a variable to which it is assigned an integer number. But anyway, this value is very important that is there for OpenSees to be able to reference these elements. And it's created automatically by STKO, but it's not regenerated if you erase elements. So for example, here I created some columns and then apparently I changed my mind a lot of times. And I got elements with indices that go from 3 to 12. This is not because of some error. It's because every time I create a new one, an index was generated, and the new index was the old index they erased was not overwritten. So what I can advise you to do if you want to erase some elements or some physical properties or some conditions, anything actually, because everything works like this. I've done it, for example, here, or of course in the geometry. In the geometry, you cannot do much about it. But in the physical property, if you did some errors, you can just change the elements like this without having to erase it. This is not really something important. It doesn't really matter. Sorry, guys, I just had to unmute someone. It doesn't really matter, but it can help you afterwards if you want to use the Python API and run some Python scripts. Sorry, does anybody want to say something? No, good. So if you want to use your Python scripts and run them over, for example, a range of indices, if your indices are not in a range, you can get some mistakes, or you will have to write them by hand, as I'll show you that I did later. So going further, we have our conditions. Conditions are not automatic in STKO and OpenSees. There's no automatic load, self-weight calculations. Whatever you put, you have to input yourself. We go in the condition tabs and we can visualize what is it that I added to this model. I fixed a few nodes. Conditions, differently from physical and element processes, are not assigned by dragging and dropping. You cannot do this. They are assigned by defining them, of course. So whenever I want to define something, I go here, constraints, single point constraints, fix, and I just will open up something like this, which is empty, that I have to fill with my options. But once I've done this, before pressing OK, I have to go and select the nodes that I want to, in this case, fix. So for example, if I want to add this node to the fix, I just will select it and will appear red in my render view visualization as I do this. And this will be applied to it afterwards. How can I see if my condition is applied? You can see now that the condition is blue. But if, for example, I go inside and I press ESC, or I control deselect everything, and I press OK, you will see that now the color of the condition changed in the work tree. This means this kind of light blue colors means that the condition has been referenced but not applied. For example, let's go back. I will just show you guys this again with something else, just to be sure it's understood, the color coding of the elements. I had these elements with an element property here. So if I go and I take my elastic element property, I select my edge and I unassign the edge. Oh no, this will not work because this is assigned to other things. But for example, let's say I clone this element. Now this element is light gray. This is because it's not assigned to any of my elements in the geometry, any geometry. When I drag and drop it, it will change its color to black. This means that the physical properties, and it's the same for element and conditions, it's used. So going back, also like fixing my condition, whenever it's light blue, it means that it's been referenced by something else, but it's not used. When it's dark blue, it means it's been used and also referenced. So for example, let's create a new condition, another fixed condition in 3D, fixing both displacement and rotation of all degrees of freedom. I give it a real name, fix not used. Oh my God, I cannot put spaces here because you're not supposed to. And then If I click OK, you will see my condition is light gray because I haven't selected any nodes or edges or faces to apply it to. So this is for you to navigate a model that's already been defined. For example, when you open up an old model, that's also very often that you find unused things. Sometimes they're there for a reason, but this color coding will really tell you what is it that it's been used, reference, or used in reference. So going forward, as I was saying, I fixed a few nodes of the model, not just the bottom nodes. Let's go back in the condition tab so you guys can see better. But also, if I orbit back by clicking my right mouse, I also fixed these nodes of the staircase because I did not apply any beam elements to the internal edges of the staircase. So I didn't want these nodes to float inside my model. And let's say the purpose of me building this geometry was just to redistribute the load from the faces to the edges, as I'm going to tell you in a minute. So conditions are our fix. I'm fixing the master nodes to the rotation outside of the plane and their translation in plane. I'm fixing and I'm applying a surface load to all the faces of my model. So this, of course, is just a simulation. I mean, this value is realistic, but it's not really what you will apply to a real building. This tool is really useful to, if you want to do like a simple, fast gravity analysis on a large building, because you can just apply a value and apply it to your faces, and the faces will redistribute the value to the edges without you having to calculate. Each load has let's say load per meter or load per nodal load, etc. So it's just an easy way for you to apply a load per area in OpenSees and STKO. Sorry, there's a few people to admit. Done. What is it that is specific about this command? If you have, for example, here, I had to divide this geometry because I wanted my mesh to have everything as one single element. So if I hadn't put this here, my face would have been made of 5 nodes, and I couldn't have a quadrilateral element when I meshed.
Un secondo che sto registrando un binario, un attimo.
There's someone with their
operativi qua.
Could you please turn it off? Let me check with these guys. Sorry.
Guys. Niente, adesso provo di partire sul programma.
Thank you. I don't know who did that, but thank you. Okay. No, there's someone else. Okay, there's no more interruption. So I was saying I have to divide my geometry here, and also if I flip around, maybe this is not the perfect visualization to see this, but I also had to divide it here. But these elements are not really, I haven't applied any physical or element properties to them. I will show you here, you will see it very clearly. This face, this portion of the slab is not divided in two by this. This is not a beam, it's just a geometric element that I did not assign anything to it. You can build this kind of stuff in your model, but either you have to fix it or join it with some other geometry. And second, if you want to use this kind of surface load, you have to define a selection set, which I haven't talked to you about yet. This is a good opportunity of unsupporting elements. So these are elements that are not going to be distributed the load on by this command. And if you select them and, for example, use this fantastic tool in the quick toolbar and just show the things you have selected, these are the elements that I have excluded from the load distribution. So I'm going to show all again. and go back to this slab to show you. I applied the load slab to all the faces of my model, and I give it a different direction compared to the global direction, and of course a value in the Z direction. And of course I'm going to project it because I have some surfaces that are not parallel to that are inclined in a different direction compared to the coordinate system of my model. So great. Another thing that I have to put in my condition is a rigid diaphragm up in the third direction applied to the interactions that I created before. And as I repeat all the time, mass and load are not the same concept in OpenSees and STKO. They're not the same concept anytime, but they're not automatically transposed one into the other. Like there's nothing inside that will do that for you. So if you want to do, for example, a model analysis, or if you want to do a dynamic analysis, you need to input your masses. This is something we see all the time, like models that we apply an accelerogram to and that we haven't put any masses, so they're not moving. So this is something you guys should remember. We applied here just nodal masses. I'll show you like this, that it's better on all the nodes of my model. Not the one at the base and not the one at the top, but yeah, just this way. So up to here, what is all that I've showed you? It's something that you do not need to care about the order you input it in. Of course, as I said, you need to have created an interaction to apply to it a rigid diaphragm condition, for example. But all of this does not matter if, for example, I don't know, this beam is under this other beam or the opposite. Instead, here in the analysis steps, this is something that you really have to care about. Before the analysis steps, there is the mesh tab. In this case, it's really easy. I assigned a global seed equal to 1 to everything, and also a structured mesh to all the faces. If you click in the mesh contour here and you change the color mode, you can see which is the type of topology and order and type of algorithm that you define for your faces or your edges or your solids, if you do have any. So before I run my model, of course, I have to build my mesh. This is something I have to do every time I change something that will change the mesh. So for example, if I go here and I change a physical property, this will not change the mesh. But if I change my geometry, I need to remesh before I run my model. A shortcut you can use is Ctrl-M to run your mesh. So the analysis steps have to be defined in a specific order, as I said. You have to first and always define a recorder. A recorder is our specific MPC recorder. I talked to you about it last time, the second week of our course. You have to give a name to your recorder and you have to define the type of results that you want. For example, in this case, I'm going to do a gravity and modal analysis. So I want displacement, rotation, reaction force, modes of vibration. And then I want the local force just to show you the graph that I can output with it. And that's it. Then we have to define the boundary conditions of our model. We have both single point and multi-point constraints. So to define some new one, you just go here and then choose a pattern, add a constraint pattern, and you will have this editor that will open up to you. This is the same for everything. So I'm not going to show you how to build the model step by step because we don't have time. But whenever you see something here, it means that you can find it in one of these lists. So just explore. This is very short, so it will be fun. It will be easy. But I don't know, for the element of physical properties, there's a lot of more options. Anyway, if I have 3 conditions, I add 3 lines and select my conditions here. In this case, I had just 2 and one for the rigid diaphragm. Same goes for my loads. So my loads are the same. It's a constraint, but it's a load pattern. And in this case, I really have to have defined my definition, my time series. So the time series I will use to apply this load, generic load, surface load in my analysis. And then I have my analysis. So in this case, the only thing I changed from the basic setup of the static analysis command, like when it's open, it's that I use the penalty method. And then I turned on the load constant, the pseudo time, and reset the pseudo time. So what does this mean? In this case, it means that the loads and the effect of the loads will be kept constant after the analysis is run, and the pseudo time will be reset to 0. This is useful if you want to rerun the analysis and you use the same time series again. Going forward, I added an ACAN command. This is a command that it's in OpenSees. You can use a solver and ask for the number of ACAN values that you want, but you need to add a record command at the end. Otherwise, this result that we asked, modes of vibration, will not be recorded in our model. We have the model properties command. Same, we defined a file name to output them in a file, and the record command. So we're a bit like tight on time. If I merge and I run this analysis, I put it in a specific folder just to here, not to rerun on something I already ran. You guys will see OpenSees will open, my linear analysis run, and my model analysis run, and my model report is also printed in the console. What I'd like to show you from the postprocessor, I open the database that this is the one that I just ran. This is one I ran before, but it's the same. And I obtain results on my model. So the results are in the database. You can see everything that you've asked from the recorder here on the left. There's something called plot groups and plots in your postprocessor. What I just want to tell you now, we don't have much time, but it's just that you can create new plot groups, and in each plot groups, you can add more than one plot. This can be useful if you want to put something in the back or just show, for example, if I go in my editor, just only on one thing, I want to show the displacement, and I want to see the undeformed shape under it. This can be very useful. Then I have chart data. So what are chart data? Let's go, if I go in my surface plot, which I activate the editor corresponding to it by clicking on it. If instead I click on the plot group, I activate the editor referring to the plot group. So there's two of them, and you can switch in between just by clicking in the work tree. If I go here and I just show my nodes, set up maybe a better visualization, I don't need this grid. You can use what is called extraction of chart data to extract data from any of the nodes, Gauss points of or fibers in your model. We don't have fibers here, but we do have nodes. So we can ask, for example, for the reaction force in the Z direction at the base. We can go here, just like position ourselves in a parallel view, in a front view, and extract all the value of the reaction force from the bottom. Let's just keep them separate, give it a name. Oh, yeah, too many nodes. But anyway, this is how you can extract chart data from your postprocessor. So just quickly, I'm going to show you the next model that we did starting from this one. And then we're going to just leave space from questions because this lasted a bit more than I expected. The second model that I can share with you also on the chat is called exercise 5. Let me share it with you guys. How do I do it? I think I got yeah, I have to exit this and just go here. Yes. Did you guys receive the model? I hope so. I cannot see your faces.
It seems like it's sent, Francesca.
Very good, thanks. So we have, from the model of before, we just changed a few little things and defined a nonlinear model. So we defined two materials, concrete and steel. Just to show you very fast, you can input your parameters and then you can use the tester to just check what's your material behavior and, I don't know, play around with it to see what happens, just like by putting a bit more hardening, for example, in it. Then we defined rectangular fiber section. In this case, I did not reselect all the beams. I could have not reselected all the beams. I could have just, changed the elements from the one of before. We created rectangular fiber sections by defining corner rebars and like all the rebars, all the materials. And we had to define this GJ parameter for everything. Now it's in OpenSees, it's obligatory to input it. And to do that, we use this very, very quick script that also you will receive. It's the same as the one that I've shared with you last week, last week of the course. We're just defining Young modulus, calculating the shear modulus from it, and then casting, let's say, transforming the fiber section in elastic section to extract our inertia and making the operation inside of it, assigning this property to the appropriate metadata. So this is our metadata that we want to assign to GJ. And as I showed you before, for example, here I had a problem. My index was not, it was not in order. So I couldn't make a loop I could have made a list of my indices to actually apply to it. But anyway, if you keep your model clean, it's a bit better. Then from the rectangular fiber section, of course, we needed an element property to assign an integration scheme. And each bin section property has a tag to the rectangular fiber section of reference. And of course, we had to change element from the elastic one. We choose the bin column element. All of these did not change. We just added an horizontal load. Another thing I can show you here, for example, the horizontal load is applied with a function that is a function of the height of the node to which is applied to the master nodes of each diaphragm. I had to create selection set for it. So I have a selection set of master nodes. I can just show you these. And you see, this is the force I applied. It's not really visible. So I can go here and make it bigger in the condition scale factor. And you will see that I have an increasing force that is a function of the height of the node. So this force is there so that I can make a pushover analysis on this model. In fact, after all of these steps that we already talked about before, I add my horizontal load with the same time series that I have used for the vertical load that I can reuse because I reset the time, the pseudo time step. And then I define the analysis, the horizontal analysis, which is a displacement control analysis with a specific control node, which is the top node. And in the first direction, so in the x direction with a target displacement of 1 meter, which is a lot. But it's just to show that the model will, let's say, yield the pushover chord. And also there's something new. I also input a monitor, which is a tool that you can use to plot a graph of results in the meantime that you're running your analysis. So I'm just going to show you this really fast, how it will look like when you run it. It will open OpenSees, run your first linear analysis, and then start to plot your, it's already there because I already put.
Because there is a subfolder.
Okay. Okay. I have to you have to remove the previous subfolder, otherwise it will just show you the previous graph. Just be sure of this.
For example, if you can choose this is the author.
Oh yeah.
It's not the other one.
Yeah, this is the one I'm actually showing, of course. I did not expect this to happen. Okay.
Before you run the analysis into the output directory, now into the up directory.
Okay.
The output as a subdirectory.
Okay, so there you go. This is our nonlinear model running and our pushover curve plotting. Displacement at the base against reaction force. Displacement at the top against reaction force at the base. You can see here, I had to define a specific selection set for my top nodes and from my bottom nodes, base nodes, and apply a scale factor to make the graph plot. Let's say.
I think you have to change it because the reaction is put at maximum. Instead, the reaction should be sum.
Sum, okay.
Yeah, because you want the total base reaction.
Okay.
Instead, the top one is the same because it's just one node.
I put all the top nodes, so maybe it's not the right one. In the selection set.
You have many nodes.
Mm-hmm.
Okay, so you can put the
Maximum, exactly. This was my idea. So to actually just show the maximum displacement.
At the bottom, you need some, so you
Mm-hmm.
not of this here.
Okay. Just this I did because I didn't know which node will have the maximum. I mean, maybe I did know because, of course, the one on the side to which I'm moving my building, but just in the case you don't know, you can use maximum. Okay, so I'm just going to stop here now is by pressing Control T here and just load the other database just to show you that you can load more than one database at once in your postprocessor STKO. And for example, let's say we go here and we change, we show everything, and we add a different plot, a second surface plot. Yeah, so this one is with the first database and this one is with the second. So if I go with model stage 1, which is the linear model, I have different, of course, displacement magnitude. One is linear and one is non-linear. But then I can see, for example, you can see that the first model stays there and the second model moves, given that I applied a pushover there. So I have many more things I can tell you about this model, but I think we can stop here. I've said everything I wanted to, at least the basic things. If you guys have any questions, I didn't explain in very detail how to build this model. So if you want to ask anything about it, there's also, as you saw before, there's Massimo here. We can turn on the camera to show him too.
Hi, Francesca.
Hi.
Did I pronounce correctly your name?
Yeah, Faisal, did I pronounce correct your name?
Yeah. I have a few questions. Can I ask them?
Of course.
Okay, so how can we pan the model, like move the model?
Yeah.
I was unable to move the model.
So I'm going to share my screen again. Going here in the preprocessor. You can pan the model by clicking on the wheel of your mouse, and you'll be able to just move horizontally.
Actually, it is on some of the first pages of the
manual. Yeah, and it's
basically
also here.
Everything with the mouse and with the central button pressed, and you move the mouse, you have the pan. Otherwise, you have the right click, the right button, click, then you can rotate the model, so you can do the orbit.
Yeah, I'm trying to share it, but yeah. Here it is. So, yes, exactly. So with the right click, you can confirm, terminate a command and orbit through your model. You can orbit also by using your mouse wheel and the control button, and you can pan with just the mouse wheel. And all of these other are shortcut keys that can be useful. These ones, of course, depending on your computer, you will have to click on function F2, function F3, function F4 to actually activate them.
Sorry, I just wanted to say we can't hear Massimo very well.
Thank you, Hannah.
Yeah, here I am. Can you hear me better now?
Yes.
Okay, I have some questions like how you change the extrusion of the model. It was 3D and then you converted it back to lines in the model. Yeah, now it is line diagram. You extruded that.
Yeah, there are actually two ways. Yeah, there are two ways. By default, in STKO, the visualization is given by the current context you are in. For example, if you are on the tab geometry, you see the basic geometry, so lines and surfaces. If you go in property, then you can see the extrusion because you're visualizing the physical property, and the extrusion of the cross section depends on the physical property. So this one is the default behavior. For example, if you go in condition, you see the basic geometry plus the boundary conditions. If you go in mesh, instead you see the mesh. This is the default behavior. If you want, you can change it. For example, you can click there in the display option, you switch off automatic, and then you can decide what kind of style you want to visualize. For example, if you want to visualize except for mesh.
Okay.
Mesh will always be a mesh. But if you move on the other
like for example,
tabs,
if I go here, I will see my geometry extruded.
Even in the geometry tab. So by default, the visualization depends on the current context. If you want to always see the extrusion, even when you're drawing your CAD, you can go there in the display options and change from automatic to one of them. Okay.
Okay, let's say now I have made this model. I have copied this model on my computer. Now, can I edit a node? Can I shift its position? For example, if I select one node and I want to change its position to from the graphics.
Yeah, actually, it really depends. Yeah, you can change a geometry, but you cannot just move a node there and expect the geometry to change, because that node is the boundary of a surface. So you have to change your model. You can move an entire geometry, but not a single node of a sub-geometry. Okay, like that.
Like if you try to do it, you will not manage. I selected this node, I move, I try to reselect the node, nothing will happen. This is because STKO is based on boundary representation and not orphan mesh. So whatever it is that you build as a geometry is defined by its boundaries. And you can see the structure of the things is inside of here. Maybe I can show you better if I just, for example, create a parallelism here, using maybe here. This parallelism is like enclosed inside a single geometry. It has vertices, edges, and faces. But I cannot really just take one of these nodes and move it around.
Yeah, because actually that kind of operation will change the underlying geometry. Like for example, there the cube is made of 6 faces, which are planar faces. But if you move just one node, they will change to NURBS surfaces, because they will be like not lying in the same plane. So it's not something that you can do. It's something that you do usually with orphan mesh based programs like SAP or Midas. But here it is not possible. Any kind of software where you have the geometry, you have to build your geometry. Okay, so if you want to change it, you can split your geometry with the explode command, then you change that piece of geometry and then you remerge it again. Okay.
Okay,
Can you assign a shell?
Yeah.
Can you assign a shell on one of like this is I think it is a rigid diaphragm in the model. This is rigid diaphragm. So instead of rigid, if I want a slab shell and I want to have UDL on that.
Yeah, you can change it. For example, in your case, you have, for example, if you want to change this kind of model for shells, you can do something like this. For example, Francesca, you can remove the boundary condition for the rigid diaphragm. The interaction, yeah. Delete. Then you can remove the floating nodes for the master nodes, because they will not be connected anymore. Exactly. Then you have all the faces that you use for the loads. You can simply create a shell material. So in this case, Francesca used the surfaces to assign the area load. But if you want to change it to shell, you have to do something different. For example, you create an element property for shell. You can use the ASD shell or the KGT, the KGQ, whatever you want. So you create a shell element and you assign it to all the faces. Okay.
I was selecting that.
Yes, like that. And this is the element property. Then you need a physical property, so the cross section of the shell. Now, to make it simple, you can use the elastic membrane plate section, or you can even do it nonlinear. Like there is the layer shell, which is the counterpart of the fiber section for the beams, where you can assign different nonlinear materials.
But for this, you have to define a material before.
Yeah, you have to define a 3D material before, which is nonlinear, and then you define different thicknesses.
For example, you have, I don't know, 6 levels, 5 levels of 1 millimeter. And then we'll have 5 of a nonlinear material.
Well, that being said, the option here is to create a shell section, and then you assign the shell section to the geometry. And then the ultimate thing you need to do is to mesh your surfaces, because now they are meshed with a single element, but this is not fine for shells, because beams, an entire beam or column can be discretized with just one force-based element that will lead to an exact result in certain circumstances. But this is not possible for shells, so you will need to mesh your model. Okay. But actually, yeah, this is not important if you go into the details, because if you want to understand how to create nonlinear shells, we have one of our previous e-learning where we explain how to analyze a reinforced concrete shear wall. And for that reason, we used shell elements with a nonlinear cross-section, with a nonlinear concrete model, and steel rebars. Okay, so if you want to know how to use shells in OpenSees, you can just go there. I think it was one of the first webinars. It was go down. RC shear wall is the number 6. So if you watch that, you can see how to create a shell element, how to assign nonlinear properties to shell elements, and how to do that kind of analysis. Okay, so you can copy the same concept that you see there, and you can apply them onto the surfaces of your slabs. It's the same concept.
Will this require meshing of
yeah, of course, as I said,
and slab? It require the same nodes for beam and slab and
yes.
And shell.
Yes, and actually this will happen automatically, because the shell, the slabs, and the beams, they are in the same geometry. So, for example, the beam edge is an edge of a surface, of the surface of the slab. So you cannot assign different element sizes in that case. So STKO will do it for you. If you mesh your slab with a finer mesh size, also the boundary edges of that slab, which are your beams, will be discretized accordingly. Okay. And the same concept actually can be seen in that e-learning course, because in that e-learning course I was modeling a shear wall with a face, with a surface, and then the two boundary edges were modeled as fiber beam sections. So it is completely the same concept. You can see the shell in the middle and then the boundary edges, which are beams. So you can just look at that webinar and apply the same concepts to the slab surfaces of this model.
The features you mentioned load slab and unsupporting, are these STKO features, or
Yes.
are they available in OpenSees as well? Are these
No.
STKO?
Yeah, they are only in STKO, because in OpenSees you have distributed loads on beams. Okay, so the LA load is on beams. Then in STKO we created a feature that is actually just an automation. So here you look at it as a slab load, but behind the scenes, this Python script takes the area of the slab, do some computation, and creates LA loads on the boundary beams according to the tributary area of the slab. So if you show them, yeah, the analysis step file, you will see that actually there is no new element, new load in OpenSees. It is just a set of line loads computed from the slab load that we have in STKO. Because unfortunately in OpenSees there is no area load for simulating slabs. You see there? You see, it comes from the load's generic surface load, but then it is just a Python script that behind the scenes takes the surfaces, computes the area, computes the tributary areas for each edge, depending on supporting or non-supporting beams and so on, does all the calculation, projection, and then at the end, it writes the equivalent LA loads on the boundary beams.
They can even see the surface load command, no, in Python.
Sorry?
They can see the surface load command.
Yeah, they can see how we do it. For example, if you go in
OpenSees solvers.
No, not in OpenSees
No.
solvers. It is in STKO external
Yes.
solvers.
Here, I'm just here.
Yes, STKO external solvers.
Yes, here and then here.
OpenSees conditions.
Conditions, no.
Generic
Here it is.
surface load. Then you can open it with a text editor, and you can see all the calculation. Well, this is pretty complicated because there is a lot of code there. But then at the end, we take the surfaces this load was applied on, and then based on the user input and the geometry features, yeah, we do all this calculation. And finally, what we write is an LA load. It's not an area load because there is no area load in OpenSees. Okay.
So for shell, we will use this one?
No. For shell, you have to use phase forces.
Phase forces, okay.
Yeah, because for shells, also that one is an automation that we have in STKO, because a phase force is a pressure, so a load per unit area. You apply it on the surface, and then STKO will compute the equivalent nodal loads doing the nodal lumping. So for the same reason, basically, because in OpenSees you don't have a surface load. Okay.
In this case, the surface load is just for you not to have to calculate by hand all the edge loads in each of your frame elements if you have a large 3D structure. But of course, for example, in this case that I showed you, you will not be able to discretize your structure. If you want to create a finer mesh, for whatever reason, you cannot do it because you will then have some nodes that are, for example, in the middle of the slab, and I have not assigned any elements to them, and they will not know how to behave. So
instead, you have to mesh it if you want to use the shell approach. Okay. So if you want to use the rigid diaphragm approach, you don't have to mesh it. So these surfaces are only used to transfer the load from the surface to the boundary edges.
And you can also do without them.
Yeah.
You can just apply the edge loads if you want to calculate them by hand, if you have other loads that will.
Instead, if you want to use the shell approach, you take those surfaces, you discretize them, you assign an element, a shell section, and then you apply a phase force on that. And finally, you discretize it based on the kind of analysis you have to do.
Okay, one more question. Can we make this model from scratch, like 4 columns, beams, and slab, just one slab from scratch? Or is there any tutorial on that?
Of course there is. There are many. So you can just go on our website here.
Yeah, actually all the very first tutorials I used to create models step by step. Okay.
Yeah.
Then I stopped because actually creating the CAD models takes a lot of time. So in the latest webinars, I'm always trying to show the model that is already there, and I explain you how to put the OpenSees stuff on it. But if you want to understand how to use the CAD modeler, you can have a look at the first webinars.
And there's also this one, not many people know it's there, but if you go here, there's university courses.
Oh yeah.
And so here we did Massimo did. For example, this one, where are the videos? Oh, down here. So here it's much, for example, lumped versus distributed 1D. This one, it's like you create the models by yourself, and also the shear wall.
Yeah, also the shear walls with micro modeling were created step by step from zero. Okay.
Thank you. Thank you.
If you have any questions, Faisal, when you create your geometry, just post them in the forum.
Can I ask one question, please?
Of course.
Yeah.
Okay, thank you so much for your very nice presentation. My question is about the control node and the monitor command. For example, if I have a very simple one bay single story portal frame, and I am using like pushover analysis, in that case, yes, it would be easy. But for example, like in the case you showed the complex structure, multi-story structure, and if I am doing the pushover analysis, And in the control node, maybe like in the simple case, I would have the force like pseudo time and reference force. But what would be the case if I am applying on the real forces? I mean, how I will monitor the pushover curve if I am applying the real forces on the nodes. What would be the command of that control node? I mean, in x-axis we will for sure we will have the displacement, but in y-axis, if I am not using the reference forces, if I am using the actual forces, what would be the command in the y-axis? What would be the value?
Actually, they are the actual forces, because in the y-axis, Francesca selected the reaction forces not at the control node, but if you show them the selection set. The selection
set here.
Yeah, she created two selection sets, one for the control node, and that will be used for the displacement, so the x-axis of the graph. And then she created another selection set, which is called base nodes, that has all the nodes at the base. So all the nodes that will develop reactions. Okay. So when you go into the monitor,
I want to just show you here, the control node is the top node.
Yeah, the control node is the top node because it will be the one that
moves more.
Yeah, will displace the most. And then here in the monitor, she selected for the x-axis the selection set 9, which is top node.
And as Massimo said, maximum is like.
Yeah, because she selected more than one node. But if you select only the reference node, so the same one you use for the pushover analysis, you will see exactly that.
Control nodes, I would have put just some.
Yeah, instead in the y-axis, she selected another selection set, which is the base nodes. And the output that she's trying to grab from OpenSees is the reaction forces. So what you are monitoring there is the actual total horizontal load, okay? Not the reference one. It's the total horizontal load, which is basically the reference one times the pseudo time step computed by the displacement control analysis, okay? So reference load times the load multiplier, which is the total load applied. And in fact, she multiplied everything by -1, you can see there. So instead of looking at the reaction, you see the total force applied, which is the same thing, basically, okay?
Thank you so much, yes.
Thanks to you for the question. We had actually a question like this in the forum a while ago, so.
I do have a question.
Yeah.
Go for it.
When I perform a pushover analysis, do the software recalculates the nodal loads redistribution based on the deformed shape, or is it inside the, I mean, your routine will calculate each, for example, the surface load redistributed on the beam elements for each time step, or is it inside the OpenSees software?
Oh, okay, so let me see if I understood your question. So the load that you apply, they are just in space, they are constant. They change in time. They are called conservative loads. If you're talking about the only load that can change their direction in time, they are actually nonlinear loads, but they are not available in OpenSees because they generate nonlinearity. They are called follower loads, but typically they are used only in softwares like in mechanical softwares where you have very large deformations. So if you have, for example, a load acting on a beam and then the beam bends a lot, and the load wants to remain constant to the normal of the surface, so normal to the surface, and the beam bends, the direction of the load should change.
Yeah. Because I'm studying stability, so.
If you want to, actually, OpenSees is very flexible. So OpenSees does not have a moving load inside, so something that changes during the iterations. Mm-hmm. But there is a way to simulate this in STKO and OpenSees. But you have to do it in an explicit fashion. For example, you can change it step by step, not during the iteration, because it can be done in T code. Okay. And I gave, actually, we didn't give any webinar on this, but we have the example of the moving load on the bridge. Yeah.
Yeah. So this is.
We made an analysis to simulate a train traveling on a bridge, and it is completely done in TCOL. Probably I will do a webinar on that in the next days.
Yeah, this one is here. I think it's the nonlinear time series.
Yeah, thank you. It would be amazing if you can.
Actually, I think we did it was the last. No.
This one is about the bridge with the moving. Nonlinear time is very nice, no?
No, it's not with the moving load. We have the moving load somewhere because but it was not in a webinar. It is actually on the Facebook forum. We posted it on the Facebook forum.
Okay.
We have some videos on there, but we will prepare a webinar
for you, Alessandro, and post it on our forum. Okay.
Yeah.
If you ask this question on our forum, we will share that file with you. And basically, there is a TCOL command, a custom TCOL command that defines the 4 application points of the train and of the van of the train. So the user can specify the distances between the wheels and the total duration. For example, the load enters the bridge at a certain time and exits the bridge at another time. And then we also showed how to move the load, but also the mass of the train for a dynamic analysis. So you can use the same concept to, for example, take the current displacement of a shell, okay, and recompute the normal and apply the load. So remove the previous load and apply a new load, which is normal to the surface of the shell. So OpenSees is very flexible, so it can be done. It's not directly integrated, but since OpenSees is an extended TCL interpreter, you can do whatever you want, basically.
There's a Michael Scott blog post about buffering. Did you read that? Maybe it's useful.
Yeah, also.
So there's this blog post here. I can share it with you.
Yeah, he also made an example about moving load instead of simple V. Probably it's easier than.
Yes, this is Professor Michael Scott blog.
It's the main maintainer together with Fred McCann of OpenSees.
Yeah, so I can just post this link on our chat and you can read this one. It's something they developed recently together about the backing exercise in OpenSees.
And there is another one with moving load. Very simple.
Always on its forum?
Yeah, it's always on this forum. He posted it on.
Go into stage?
Go up.
Up, okay.
No, there is somewhere. It is somewhere because he posted it on the Facebook group. Load incrementation. No, it's not there.
Anyway, there's also an index to this blog. You can find it at the bottom of my presentation here, blog index, and just search for it.
Okay, thank you very much.
Geometric nonlinear, probably there. No.
It always gives names which are very nice, so you don't really find it super fast.
But it is there because he posted it a couple of days ago on the Facebook group.
Yeah, by the way, if anybody wants, you can all join the OpenSees Facebook, and that's also a very nice place to post questions and search for other people which had the same problems before.
I have 2 questions.
Okay.
Can you hear me?
Yes, we can hear you.
Okay. Well, first, thank you very much for your help in the forum. I'm the one struggling with the sheer wall.
Yeah.
And I have 2 questions about what you have done. First of all, is I'm have this during the analysis I monitor the displacement and the base force of my wall, and I want to know how can I extract, because from the STKO monitor I can see how it's the force, well, the force displacement curve is being developed, but I want to extract exactly those values without going to the
copy paste from the monitor.
I think in the monitor we put something to copy paste it, but actually the monitor writes a file. Okay, so if you go into the directory, you have a text file.
Yes. Okay.
Yeah.
There I can know, because normally it generates this folder, STKO monitor folder.
No, that actually is just a folder with Python files.
Yeah, that's
creating the GUI. Okay, but it is not The graph are not there. The graph are in the same folders.
You give it a name. Like here, if you give it a name to your plot, you can just find it again. Like for example, here I have it. I give it a
but
name.
for example, here, which is okay, can you share your screen? Because I'm not sharing
my screen. Oh, guys, should have told me before.
Yeah, you're sharing now.
So
now go back into the folder. I want to show them.
Yeah.
So this one is the folder where you have article files. Okay, there is a folder, a subfolder called STKO monitor. That is not important. There are only Python files to run the monitor. But then here you have some files with the extension PLT, which are actually the files the monitor is monitoring. Okay.
Yes.
Just text files. So the first line is an header, okay, with the name of the two columns. Yes. Then you have two columns, X and Y axis.
But should I do something in STKO to assure that this that data file is being written?
No, they will be written by default.
Always.
Yeah.
Okay.
By default, they will have a standard name, or you can give it a username. Okay, but they will always be written. Be aware that the next time you run the analysis, the previous one will be deleted and they will be replaced by new ones.
Yes, always. But if I change the name.
Yeah, if you change the name, they will be there. Yeah. No, actually not, because actually I delete all the PLT, all the PLT file in that folder. So if you want to save them, copy them away from that folder.
Okay, before running another one. Okay, and from this because to monitor, I always do the selection sets. Mm-hmm. That in this case, you said that you were using the selection set to, for example, assign some properties to this line inside the surface load, so it doesn't redistribute the forces. How do you do this? Because I thought that this was just for monitoring things.
No, the selection set, you can think about it. The selection sets are multi-purpose tools. So the first usage can be to save time for selection. So sometimes you have to select a lot of geometries, okay? And it takes time to select all of them in a complex model. And then you need to select them again and again and again during while you're working on your model. So you can store those selections. Okay, so it can be just something useful for speeding up your workflow. Sometimes instead they are necessary. For example, the monitor requires a selection set. The region command requires a selection set. The displacement control requires a selection set. So sometimes you really need them, and some other times you can use them just to have groups. Okay, so just save selections basically.
I suggest you always use the selection set when you create an interaction before, because you will have to do it many times, like something will change. Okay. You already have a selection set, then it will be super fast to just recreate it with the same. So when you you are in your interaction, you click OK. Once you say select, you just go in your selection set and select. And then terminate the command with the right click, and it has selected all my beams at the master of this interaction. And you can do the same for the retained nodes.
So basically, when you do a complex model, if you store your selections into selection sets, it will be very handy.
Okay, perfect. Thank you. And one last question from the post-processor of this of the modal analysis. Well, the NG values analysis you did, is possible to see the mode shapes?
Yeah,
of course. So if I go,
I think you didn't ask for.
I asked for in the first model. So modes of vibration, modes of vibration.
Yeah, you have to put modes of vibration both in the result field, so you see the colors based on the modes of vibration, but also on the deformation field, because you want to deform your shape according to the mode shape. Okay, and then when you select a result, which is a modal result, so a result that has many modes, because basically in STKO we distinguish between two kinds of results: historical results, so results that change in time, and modal results, so results that are fixed in time, but they change like in a, yeah, not in time, but in the different modes. So basically the only one is the eigenvectors. And then in this case, you will see that a new field appears after the time step, which is the mode. Okay, so you can just scroll through all the modes to visualize all the deformation shapes, the mode shapes.
Just be careful, because if you make your eigen command after your analysis command, and you don't have another analysis command after that, like in my first model, if I go to the example 4, you will not record your modes of vibration result in the database. So you need to create a custom command with the word record in it. Otherwise, they will not be saved.
Yeah, this is a rule in OpenSees basically, because in OpenSees, a standard analysis does many time steps, and after each time step, it calls internally the record command. Okay, so if you do an analysis, everything will be recorded after each time step. The problem is that the eigenvalue analysis is not a real analysis. So after you run the eigenvalue analysis, OpenSees computes the eigenvalues and eigenvectors, but it doesn't use the record command. So it doesn't explicitly call all the recorders. Okay, so you have to do it by yourself.
And if you want to use the eigen command before your analysis, be aware that maybe the setup of the default analysis that is being called by the eigen command maybe is not coherent with your interactions or with the constraints that you are applying to your model. So to me, it's always useful to put your eigen command after an analysis.
Okay, so in this case, you did the analysis of the load you applied, then the eigenvalues, then the model, and then we record again.
Yeah.
I mean, this can also be useful if you're doing a nonlinear model that will affect your model properties. If you put the eigen command afterwards, this effect will be recorded. Otherwise, if you put it before, it will not be recorded.
Okay, perfect. And now this one for sure is the last question. Because I'm remembering everything I wanted to ask. In this analysis, when you set all the features of the analysis, you said something about the load constant that has to be checked with the pseudo time, and the pseudo time restart to 0 if we wanted something in particular. But I didn't understand how it worked, this load constant command.
Okay, so this is quite complicated. Now OpenSees has the concept of time. Okay, so the time that you see into an analysis is called pseudo time, because sometimes it refers to real time. Sometimes it is not a real time. That's why it's called pseudo time. So for example, in dynamic analysis, it is the real time. In static analysis, it is called pseudo time because actually it is the load factor. Okay. So how does OpenSees increase the load? For example, when you create a load pattern, you create a time series, then OpenSees performs the analysis, takes the time, the current time. This time goes into the time series function, okay, as the abscissa, and then he takes the ordinate value of the time series, and that will be the load multiplier. Then OpenSees takes the reference load, multiplies by this load multiplier, and that will be the current load at the current time step. Now the problem is that when you end the gravity analysis, you arrive at a pseudo time of 1, and all your linear time series is complete. So you apply the 100% of your gravity loads. If you do another to time 2, your reference load will not get constant. They will keep on increasing, okay, because your time is increasing. So one way to tell OpenSees to keep some loads constant is to use this command. So the load constant basically says that all the loads defined before this command, they will not depend anymore by their time series, but they will be kept constant in the subsequent analysis. Okay, this is very useful when you do, for example, pushover. So you do gravity analysis, you increase your vertical loads from 0 to 100%, and then you keep them constant. Since you are keeping them constant, you can reset the pseudo time to 0. Now, resetting the pseudo time to 0 is not really necessary, but sometimes it is necessary. For example, in displacement control analysis. Why? Well, because in displacement control analysis, the pseudo time is the real load multiplier. Because in fact, in displacement control, you don't really need a time series, because the displacement control tries to compute the load multiplier by itself. And it uses the pseudo time. So imagine you don't start from 0 like this, but you start from the last pseudo time you have in your gravity analysis. So you start from 1. Your pushover analysis will not start from a 0 horizontal load, but will start from a 100% horizontal load, and it will grow up, okay? So that's why it is always important to reset the pseudo time step to 0, especially in displacement controlled analysis.
Like specifically in the other example, the same time series that I've used as a load ramp in the gravity analysis, it's used in the displacement control analysis too. So it's like the same.
Yeah, in the displacement control,
No,
actually,
it doesn't use the ramp. Okay.
You have to use the time series because the OpenSees commands require a time series, but it is not used.
Okay.
Okay, so it can have any shape, but it will not. The displacement control analysis will not
follow
use,
that.
Yeah, will not ask the load multiplier to the time series, but it will take the current pseudo time step as the load multiplier. Is it clear? It is a little bit confusing, but
No, but now it's better. Now it's better. Thank you.
It's called time, but it's not just time.
Yeah, in fact, if you monitor the time into a displacement control, you will see that the time is not monotonically increasing. It can decrease because it is actually the load multiplier. Okay, so it will increase up until the reference load can be increased. Then, if you have softening, you will see that the pseudo time goes back because actually it is not a real time. It is the load multiplier. Okay.
Okay, thank you very much.
You're welcome.
Hello, I have I think three questions. And I think two of the questions might be that I'm getting ahead of myself. But the first one is going back to the shell elements that you represented here in your model. It's indicated that that STKO does like a Python scripting to get the loadings to the elements that are bar elements that are on the perimeter of the shell. But I'm seeing some elongated shells and also some square ones. So we got a two-way and one-way type shells in this case. Is the script able to identify these elements as being one-way and two-way? Or we
see that.
Yeah, in this case, I chose to do just a one-way slab.
Oh, okay.
But if you want, you can choose two-way.
You can choose two-way, and but then you will have to select the ones that you want to be one-way and two ways.
Yeah, for example, if you have some slabs that are one-way and some slabs that are two ways, you create two different boundary conditions. So a surface load for the one-way and another surface load for the two-way. And of course, you can select the orientation probably.
Yes.
Remember.
You can change the direction that you want. But also you have to be like the reason I chose one way in this case is because some of my slabs, you can see it from the property assignments, do not have elements in both of the directions. For example, the ramp here, it's all transparent, maybe just try. For example, the ramp here only has elements on one side. So for me, it has to be one way, otherwise it will not compute.
Yeah, but if you have a face with all the boundary edges that have a beam property assigned, then you can use the two-way.
Okay. Now that's my first question. My second question, I think I'm getting ahead of myself. We also have a situation where we calculate or we need to calculate the shear base of the building. And also we get participation factors regarding the mass that will be participating if we do an analysis that is a seismic analysis. And also the third question will be the participation factor, the period, the fundamental period of we're going to get it. to that point, or
you actually have them in the model properties. I think you show them the model properties.
Yeah, I also printed them in this file.
Yeah, the model properties command does, you can choose it, it is optional, but you can choose to print it on the console, but also to print it on a file so that you can look at it later on. And in this case, it will print a so-called model analysis report. It says what is the domain size. Now in this case, it's a 3D problem. Then it gives you the eigenvalues for each mode, which is lambda, then the omega, frequency, and period.
Right.
Then you have the total mass of the structure. You have the total mass of the structure at all nodes and only at 3 nodes, because sometimes you want to know what is the total structure, the total mass of the structure, and sometimes you want to know what is the total free mass of the structure, so the mass that can be excited. Then you have the center of mass, and then you have the model participation factors. This one actually is the only output that can change if you, depending on the eigenvector normalization. Okay, and this depends on the eigensolver you're using. But in STKO, we can choose to force the well, basically, okay, if you're interested in what kind of eigenvector normalization OpenSees uses, if you use the gen band ARPAC, which is the default, it does a mass normalization. So the eigenvectors are normalized such that the eigenvector transpose times the mass times the eigenvectors, which is the generalized mass matrix, is the identity. Otherwise, you can use the if you use the LAPAC solver, it does a displacement normalization. So it normalizes the eigenvector such that the maximum component is 1. So actually, the problem is that you don't have any freedom on how to choose the eigenvector normalization. So we gave actually an option in the model properties. If you open the model properties command, you can choose to force a displacement normalization. For example, if you're using the general band ARPA, which is the default eigensolver, remember it gives a mass normalized eigenvectors. If you click on new norm, I will print the output for a displacement normalized eigenvectors. Okay, so that is the only portion. So go back into the mass report file.
Yeah.
That is the only portion of the file that can change based on the normalization. Then you have the model participation masses by single mode, cumulative, and in absolute values or in ratios. Okay, so at the end, for example, is what you really need. The cumulative participation masses normalized, so in ratio of the total mass, as a ratio of the total mass.
You also asked about the base shear, and that's just a simple extraction of a result.
Yeah, you can extract the result as Francesca showed before, or using the monitor, so you can grab the base
example,
shear.
you can just go here and just on the nodes select. Now in this case, we don't have horizontal forces in this model, so oh yeah, I can choose the other one. Yeah, for the model stage 2, I did a pushover.
Yeah, but you need to change the plot from this model to the other one.
Otherwise,
You
it
have
doesn't
to
have
select
the yeah here. So I get reaction forces from the x direction. Select all the base nodes. Yes.
Okay, let's assume you have selected all the base nodes. Then you click on next.
And I can just sum them.
Sum, because you want the total base reaction. Then it is giving you a graph, but if you can look at the last value.
Just go here and this
that
is
one,
your value.
yeah, that will be the final base reaction.
Okay. Yeah, I'm asking the question because I got disconnected, I think, in the middle of the presentation, so I didn't see all these pointers that you're
The model report, yeah.
Okay, thank you very much. I think you answered the question.
You're welcome.
Anyway, the webinar is recorded, so if you miss a part, you can just rewatch it. It will be on YouTube by tomorrow.
Okay, thank you. Thank you so much.
Guys, it's like, oh, there's some other questions? No? Okay. So it's like, it's been 1.5 hours. Thank you guys for participating, for turning on your camera and asking a lot of questions. It's been great. And I'll see you next week on Wednesdays at the same time for our first, like, say, more theory series on geometries, local aspects, and selection sets. We're gonna just keep diving on these topics and understand some tips and tricks. If you have any questions, just post them on the forum, and all the files will be uploaded tomorrow on our website and the video on YouTube.
Thank you very much.
You're welcome.
Thank you. Thank you very much. Muchas gracias.
Gracias, Eric.
Thank you. Thank you.